So sometimes we may need to expand a power. So here we can we want to integrate secant x plus tangent x quantity squared, and you can multiply that because you could just be squaring a binomial. So you'd square the first term, get secant squared x, twice the product of the two terms secant x tangent x, and then plus tangent squared x. And then you can use this identity here that tangent squared x is equal to secant squared x minus 1, and you can replace the tangent squared x with secant squared x minus 1 right here. And then you can combine secant squared x and secant squared x and get 2 secant squared x, and then you have the middle term 2 secant x tangent x, and then you still have the minus 1. Now since when you integrate secant squared you get tangent, so this would integrate to 2 tangent x, and then when you integrate secant x tangent x, it integrates to secant x, so this would integrate to 2 secant x, and then when you integrate minus 1, it integrates to minus x, and then of course you add your constant. On this next one, I'm going to eliminate a root. So it turns out that there's a trig identity that says if you have the cosine squared of an angle, then that can be written as 1 plus cosine of twice the angle, so in this case cosine of 4x all over 2. And then if I were to multiply both sides of this equation by 2, I would actually just get 1 plus cosine of 4x is equal to 2 times cosine squared of 2x. So I can replace 1 plus cosine of 4x with the 2 cosine squared of 2x. So then when I take the square root of that, the 2 stays in the radical, and then I can take the cosine 2x out. Since that's squared, when I take it out, it won't be squared. So I have square root of 2 times the cosine of 2x dx. And actually, anytime you integrate the cosine of a constant times x, that's actually going to equal the sine of the constant times x divided by the constant. So that's actually going to equal the sine of 2x divided by 2, and then of course the square root of 2 was a constant in the integral, so it comes out here as well. So you end up with square root of 2 over 2 times the sine of 2x, or if you prefer, square root of 2 times sine of 2x divided by 2, and then plus a constant. On this next one, what I'm going to do is, this is a rational expression, so what I'm going to do is I'm going to use long division, and I'm going to divide the denominator into the numerator. So over here I take 3x, and I need to multiply, find out what times 3x equals 3x squared, so that would be this x right here, and then multiply back. X times 3x is 3x squared, and x times 2 is 2x. Well, then remember you got to subtract that, and so when you subtract 3x squared minus 3x squared, they cancel, and then minus 7x minus 2x would give me minus 9x, and there's nothing to bring down with that. So then I say 3x times what equals minus 9x, so that would be minus 3, so I put a minus 3 up here, and then multiply back. Minus 3 times 3x is minus 9x, minus 3 times 2 is minus 6, and then again you have to subtract this quantity, and when you subtract, that's going to be minus 9x plus 9x, which cancels, and then you're going to have 0 plus 6, which is plus 6. So then that means I can actually replace this rational expression with the quotient I got over here, which is x minus 3, plus the remainder portion, which is 6 over 3x plus 2. Now, we know how to integrate x. If you integrate x, you simply get x squared over 2. And you know how to integrate minus 3, you just get minus 3x. So let's focus on how we would handle this fraction here, 6 over 3x plus 2. So let's say we let u equal 3x plus 2, the denominator, and du equals 3 dx. Well, then I could write this. Let's factor a 2 out of this, and let's put the 2 out here. And now the 3 dx right here, that's the du, and this is the u. So when you integrate du over u, it's actually the natural log of the absolute value of u, and since u is 3x plus 2, we would have natural log of the absolute value of 3x plus 2, and then of course we had a 2 outside the integral, which comes in here. So I have 2 times the natural log of the absolute value of 3x plus 2 plus a constant. And so now let's just stick that in here with these other terms, and that finalizes our integral here. Okay, so now the next thing I'm going to do is I'm going to show you we're going to separate a fraction. And so what we're going to do next is we're going to take the 3x over the square root of 1 minus x squared plus 2, and then write the plus 2 over square root of 1 minus x squared. So I can break this up into 3x over the square root of 1 minus x squared dx plus the 2 over the square root of 1 minus x squared dx. And so let's do each integral separately. The first integral, I'm going to pull the 3 out. I'm going to pull the 3 outside the integral here, and now I have x over the square root of 1 minus x squared dx. And so let's let u equal 1 minus x squared, and then du would be minus 2x dx. So that I get du, I'm going to multiply the inside by minus 2 right there. And then if I have to divide the outside by minus 2, so therefore with the 3 divided by minus 2, I get minus 3/2 on the outside. Now, this numerator here with the dx, that's just the du. And then this can be written as u to the negative 1/2 power, because this is just the square root of u, but since it's in the denominator, when you put it in the numerator, it becomes u to the negative 1/2. So I have minus 3/2 times the integral u to the negative 1/2, and then just apply the power rule. And so I get minus 3/2 u to the positive 1/2 over 1/2, and when you multiply negative 3/2 times 2, you'll get negative 3, and then when you replace u with 1 minus x squared, you'll get 1 minus x squared to the 1/2, and then of course plus your constant. Now that's just the first integral. We still have to do the second integral. The second integral is 2 times the factor the 2 out, we get the integral 1 over square root of 1 minus x squared dx. Well, if you let u be x, then du is dx, so this is actually du over the square root of 1 minus u squared. So if you go back and look at your inverse trig functions, you'll see that this integrates to the inverse sine of x. So you have the 2 out here, so that's going to be 2 times the inverse sine of x plus a constant. Now, since these two were added together, let's put them together, and so we get the result we got from the first integral plus the result we got from the second integral, and then plus a constant. We don't need 2 constants. We can just say 1 constant there. Okay, now I've got one more that I can do here, and this one I'm actually going to multiply by 1. Believe it or not. So if I wanted to integrate secant x, this way you can see where the integral of secant x came from, because there's actually a formula for the integral of secant x. So this one's kind of tricky. Probably took somebody a long time to figure this out. But what you can do is, if you multiply this by secant x plus tangent x over secant x plus tangent x, then you're really not changing the value of the integral, because you're just multiplying by 1. Now if you distribute the secant x in the numerator, secant times secant is secant squared x, secant times tangent would be secant x tangent x, and in the denominator you have secant x plus tangent x. Now, let's let u be the denominator, secant x plus tangent x, then du would be, let's do this backwards, du would be the derivative of tangent x, which is secant squared x, plus the derivative of secant x, which is secant x plus tangent x, dx. So now you can see that in the numerator I have all of this. This is just du. And in the denominator, that's u. So I simply have the integral of du over u, where u is secant x plus tangent x. And when you integrate the integral du over u, you get natural log of the absolute value of u plus a constant. And then you can replace u with the substitution, secant x plus tangent x. So you get the natural log of the absolute value of secant x plus tangent x plus a constant. And so that's how these two integrals were actually derived. So when you go back and look at your formulas, you can see that, you can now see how they derived those formulas. Okay, now that's all I have on this. This was just the basic integration techniques from things that we've already learned in calculus and algebra and trig. And so in the next sections we're going to learn some more specialized integration techniques.